So this is one of my more blasphemous papers. This is probably one of the papers that's got astronomers the most upset. And I take that as a good sign. If astronomers are upset about it, you're probably getting to them. You're probably saying something that, you know, conflicts deep down with their worldview. And I think that's good in of itself, because if an astronomer or a scientist can't question their own beliefs, how do they expect to really make progress when sometimes a discovery will completely do away with that, with all your beliefs? If you just doggedly hold on to your worldview, how do you expect to make any progress? And there was a saying where it was like, the only way progress really happens is that the astronomers that hold a specific worldview eventually pass away or retire, and then a new generation is brought up with new beliefs. And that's exactly the truth. I think that's how it works. You're not going to convince astronomers that this is how stars actually behave. They're set in their ways, they have their own worldview, and to hell with any other idea that conflicts with that. But without further ado, I present Accretion and Ablation during stellar evolution. How old is Mercury? I'll link this to the bottom. Basically, the reason why I wrote this paper was that since stars are around for extremely long periods of time after they're, fully dead and they lose their magnetic field, there has to be a way to make them smaller and smaller and smaller, thus increasing the relative size of the core versus the outer regions. For instance, you have, I'll scan this and put this in the version 2 of the paper, but here's Mercury, here's the Earth, and all that swiped away material is all the material that that's going to be ablated away from the Earth. And I use Mercury as the backdrop for Earth. When Earth eventually dies and all its material is ablated away, because Mercury and Earth's core sizes are roughly the same. They're not exactly the same, but they're about. I think the diameter of Mercury's inner core is around 2,000 miles or kilometers, and then Anyways, they're about the same size. I can't remember the exact numbers. I'm gonna mix those up in my head. But basically, I took the axial angular momentum, and I did these equations. Of course, 2/5 or 0.4 is a undifferentiated object, spherical object. Of course, that's not correct, specifically nitpicky correct, but it's a good way to get a ballpark estimate. So I took Mercury's mass, its radius, and I calculated its moment of inertia, and then I calculated its angular velocity, and I multiplied those together. And when you do that, you get what's that? L. That's the total axial angular momentum. So 9.712 times 10 to the 29 kilograms meters per second. And I took that amount and I juxtaposed that to the Earth's total axial angular momentum to get Mercury's age, because it takes a lot of time for that thing to slow down, to stop spinning. And the principle is quite simple. And I've been receiving lots of ridicule for this too, but it can be understood quite easily. Outer space has very little friction. So when something is spinning in outer space, there's not a lot of stuff out there to slow it down. Versus if you were to take a bicycle tire and you spin it up real fast with your hand, or like what I used to do as a kid, I used to flip the bicycle upside down and I would crank the pedals as fast as I could just to see the tires spin extremely fast, and I'd be scared to touch it because it'd probably rip the skin off your hand. But eventually the friction of the gears and of the bearings, as well as the friction between the wheel and the air, will slow the tire down. Meaning, the tire will spin really fast when you get it spinning up, but then as time goes on, it starts to slow down and slow down and slow down, which means the slower it spins, you know that it was spinning really fast previously. It took time for it to slow down. And the same thing with the total angular momentum of an object. Now, it's more complex than that, but the basics are there. If you have something that's not spinning very fast, if it's spinning extremely slowly like Mercury and Venus are, and Mercury's unique thing is not only is it spinning extremely slowly, but its core is about the same size as Earth's inner core, and it has had all of its material ripped away. So how did all that material get ripped away? Well, it was ablated, and it takes a lot of time for that to happen. And to really get a grasp of the age differences between these objects, and trust me, I remember the day when I did this, I was like, holy crap, Mercury is really that old. I have the sun about 100 million years old. I have the Earth as 4.5 billion years old, and Mercury is 32 trillion 750 billion years old. And you can go ahead and plug those numbers in, and you'll come out with the fact that Mercury is 327,500 times older than the sun. So 1/3 of a million times older than the sun. That should give people a bit of perspective of how old the universe really truly is. And also it kind of flies in the face of the Big Bang creationism thing, because how can the entire universe be 13.7 billion years old and have an object in it that's many trillions of years old? It flies in the face of that specific worldview. But put simply, all my people, we already know the Big Bang it's kaput. It's like a creationist argument that was cooked up in like the 1920s or 1930s, something like that. We can ignore it. It's much better to look at these objects and try to wrap your mind around how freakishly old they are. As well, another point I wanted to bring up, and this is in the paper, but that Mercury has been dead, just completely geologically inactive for the most part. It's his whole existence, like 99.99% of its existence, it's been dead. And to put that in analogy form, I would say it's like say a Tyrannosaurus Rex. Say you have a nice large T-Rex running around looking for food. I don't know how old dinosaurs got to be, like a Tyrannosaurus Rex. I would say, okay, 100 years. A T-Rex could be about 100 years old. Now, when it dies and then it gets covered and becomes a fossil over many thousands of years, it stays a fossil for hundreds of millions of years. I don't know, T-Rex is 145 million years ago, something like that. But it's been a fossilized T-Rex for a hell of a lot longer than it's been running around. Max, maybe about 100, maybe about 150 years. I don't know how old those creatures live to be. But that's many magnitudes longer than its active state. And the same thing with Mercury. Mercury has been dead for many, many magnitudes longer than it was alive. And that's a very important point to bring up, because it's a different way of looking at the solar system objects. They're all in different stages of evolution. They all were adopted by the sun being the youngest object in our system. And these objects in our system don't have limits to their age. Uh, it's easily reasoned that if you were to break up Mercury into smaller and smaller and smaller bits, you're gonna have pieces of Mercury floating around as asteroids and meteoroids that are gonna be even older. There are probably stars out there that have broken up into bits and pieces that are floating around and as meteors that enter into Earth's atmosphere that are quadrillions of years old, that have just been in outer space just for essentially eternity, because a lot of the material that's out there is radiometrically stable. It doesn't decay. Anyways, I think I made this video long enough. I'll link this to the bottom. But it's a good exercise, a mental exercise, to really understand how grand the universe is. The fact that astronomers still struggle with the very basics is telling. And it's about time that we stood up to them and called them out on it. Because you can't sit there and make all these observations and then continue teaching a worldview that doesn't make any sense. And that's what they're doing these days. And it's not good. It's not good to hold on to ideas that no longer make any sense, because it's just like it ruins our future, the possibilities that we have for exploring the galaxy, for understanding what's actually out there. All right, you guys, take it easy.